We want to find let R be the region under the graph, y is 4x minus x squared above the x-axis. So it looks something like this. And we want to find the volume of the solid obtained by revolving R about the y-axis. So can you visualize that? Can you see the shadow on the other side as all of this rotates around? It's kind of like a cake. We're going to focus on a point X, which is here. We're going to draw a little box a little bit to the left of X, a little bit to the right of X. And when we rotate this around the axis, we're going to get a cylindrical shell. And the question is, what is the volume of that cylindrical shell? That's what we want to try to visualize. That's what we're going to be looking at. The thickness of this, we'll call change in X. That's going to be important. And we want to identify what the volume of that shell is going to be. Now, we have a shell here. So let's draw a similar version underneath, approximately the same size, just to help us see this. Here's the axis of rotation. And there is my X. It's a little hard to see, but we have two cylinders. We have the outer cylinder and the inner cylinder. To go from here, the axis of rotation, to the outer edge, that's big R. So from here to here is big R, and from here to here is little r. That's going to be important for us. And the volume of that shell, what will the volume of that shell be? The big cylinder minus the small cylinder, pi big R squared h minus pi little r squared h. And what do we get? Factoring out the pi h, big R squared minus little r squared. Volume of the shell, pi h, that's big R plus little r, and big R minus little r. Now, we already noticed here, big R is from there to there, here to there. That's big R. Little r is from there to there. So we can see that big R minus little r is that thickness. Big R minus little r is simply going to be the change in X. So we have that, which is nice. But the hardest part to think about here is what is big R plus little r. So again, let's make sure we can visualize our picture. Focus just on this part. X is in the middle. Directly in the middle is what it should be. My picture is not great there, but from here to here is big R. From here to here is little r. So you can see that big R plus little r is essentially 2x, or if you like, x is the average of big R plus little r. Big R plus little r over 2, the average of the r's is x, so 2x is big R plus little r. That's the one thing that geometrically is a little challenging here. So you get the volume of the shell in general is pi h, which will be the function, the value of the function, right? We have our function here is 4x minus x squared, but in general, it's y. Height is going to be y. R plus r in general is going to be 2x if we are rotating around the y-axis. You want to keep those things in mind. So in this example, the y value at that x is 4x minus x squared. So the volume of the shell is pi times 4x minus x squared. The y value, that's the height, times 2x times delta x. That is one shell. It is one shell for us to work with. But remember, we have an infinite number of shells, but let's start with a finite number of them. So thinking about this, here's our picture. We picked one value of x to get this shell. We could have picked another value of x to get this shell. And imagine going all the way across and doing n different ones as we're doing this, right? You get the idea? So the volume of a single shell, fine, we have that. The volume of a single shell is pi times 4x minus x squared times 2x times the change in x. What's the volume of all shells? So in this case, maybe n of them, all n shells. That's the sum of all of them, sum of all n of the shells of pi times 4x minus x squared times 2x delta x. And then what do? We go from n to infinite shells, or actually getting the volume of the entire solid. So what is the volume of that solid? That is the integral. What integral? Integral of what values of x? Remind ourselves of our image. This is what we're working with. So my x values range from where to where? X values range from 0 to 4. So x values range from 0 to 4 of all of this. Pi times 4x minus x squared times 2x. And then as we shrink delta x to 0, as the number of boxes goes to infinity, delta x becomes dx. And this is the integral that we have to evaluate to find the volume of the solid of revolution. But again, it's important to me that you can visualize this, right? Visualize what's happening here. We have a cake-looking thing, maybe, or a Jell-O mold-looking thing. But this part here is missing, right? And this is coming all the way around to give us our solid of rotation. Okay, so we've got our integral. Let's write that down and evaluate it quickly. Volume of the solid is the integral from 0 to 4 of pi times 4x minus x squared times 2x dx. Let's pull out the 2 pi. And I have the integral from 0 to 4 of 4x minus x squared times x dx. So we get the volume of the solid is 2 pi integral from 0 to 4, 4x squared minus x cubed dx, which is 2 pi antiderivative 4x cubed over 3 minus x to the 4th over 4 as x ranges from 0 to 4. Which gives me 2 pi 4 times 4 to the 3rd over 3 minus 4 to the 4th over 4 minus 0 minus 0. Nothing happening there. So what does that give me? Volume of the solid is 2 pi times what? It looks like 4 to the 4th over 3 minus 4 to the 4th over 4. And what do we get? We get 64 over 3, if I've done that correctly. So multiplying all that, that's going to give me 128 pi over 3. And, you know, for something like this, it's a good idea to check your work. So let's go ahead and feed this integral in either to the graphing calculator or into Wolfram Alpha or something like that. So let me do that. So jump into Wolfram Alpha. What am I going to say? Integrate my function here is pi times 4x minus x squared times 2x dx, whoops, capitals, as x goes from 0 to 4, And let's see what Wolfram Alpha says. 128 pi over 3, which is what I thought the answer was. So I guess that looks correct.